Good morning, friends and dear students. It gives me immense pleasure to be here for my course, Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. I am in the process of my course, Engineering Thermodynamics. As of now, I have completed all the module 5. Also, I have done some 15 lessons of numericals. Then I have completed the definition and the terminology. Today is my discussion on question bank of module 1, that is basic concept and first law of thermodynamics. In this I will be discussing about basic concepts and some of the laws of thermodynamics. So here we have some heat and work. Then we have zeroth law of thermodynamics, first law of thermodynamics, properties of substances. I will go with the question number 1, that is the differentiate the system, surrounding and boundary and explain in detail. But this is my question number 1. So for the thermodynamic point of view, where the gases or substances are working, in that a closed area is called the system, and beyond that it is called the surrounding, and the limitation between the system and the surrounding is called the boundary. So the boundary is an imaginary line in which the system and the surrounding can be separated. So this I will go one by one. A system is defined as a quantity of matter or the region in space chosen for the thermodynamic study. The mass or the region outside the system is called the surrounding. The real or imaginary surface that separates the system from its surrounding is called the boundary. So this you can see here, that how we can define the system and the surrounding. So a system is defined as the quantity of matter. So you can see here there is a one system with a blue color, and this system, or it is in the some region, and this region is somewhere, it is shown as a blue color here, and from here there is a line which is separating this system from the surrounding. For this case, here is the surrounding, and this system will interact with the surrounding here. So in the surrounding, heat and the work can be transferred. And here, if you see, here is a boundary, that is called the isolated boundary. If you make like this, means heat and work will not transfer out of this. But there is one more boundary here, that is called the system boundary. This system boundary is separating from the surrounding boundary. So the system is different, surrounding is different, and there is a combination of this both, it is called the universe. So if we take as a whole this as a system, and here is the surrounding, so this is the your boundary, and this is the isolated boundary. In this work and heat, this heat will not transfer from here to here or here to here. So that is the system, surrounding and the boundary. Here we can see the system boundary. A boundary is closed surface surrounding a system through which energy and mass may enter or leave the system. So the here if you see the boundary, in this boundary if you see that from here the mass, energy and mass. So from the system, energy and mass may come for the open system, but for the closed system, mass will not transfer. It will not cross the boundary. So that is the for that. So now what is the surrounding? Everything that interacts with the system. So this is the system and here is the surrounding, and this surrounding is interacting with the system is called the surrounding. And what is the system? A system is a region containing energy and or matter that is separated from its surrounding by arbitrarily imposed wall or the boundary. So a system is a region. So here it is a blue region. It is shown as a system. From here the energy and the mass or matter that can be transferred to the surrounding, and there is a line which is separating the surrounding and the system. It is called the boundary. Now I will discuss about the question number 2. Write the zeroth law of thermodynamics. So this zeroth law, actually it is developed very last. First was the first law, then the second law, and after that third law, and after that it is decided that there is one more law which is called the zeroth law of thermodynamics. This zeroth law of thermodynamics is related with the temperature. By virtue of this, we can measure the temperature by putting different type of material like mercury or some other gases inside a glass tube, and if you heat or if you want to measure this thing, the expansion of the volume of that glass inside the glass tube will give directly the temperature. So this method was very much useful, and this was developed after third. So what name to be given? So a scientist community, they have decided that we should give this name as a zeroth law because it is falling before first law. So the first, what is the number? It is 0. So they have given the zeroth law as a name. So here it is stated in this way. The zeroth law of thermodynamics states that if two bodies are each in thermal equilibrium with some third body, then they are also in equilibrium with each other. So if we have the two bodies A and B, and A is equilibrium to B and A is equilibrium to C, so B and C will also be in the equilibrium. So that is the concept of this zeroth law of thermodynamics, and it is by this way we can find out the temperature of the any system. So if you can see here that there is a body A. This body has a thermal equilibrium with body B, and this A body has got the thermal equilibrium of the C. Without touching this, we can say that body B and C are also in the equilibrium. So that is the concept of measuring the temperature. Measuring the temperature, which we normally see in the doctor's hand to measure your fever and all. So if you put the thermometer in your body, so your body and the glass A and B, and the mercury is a C. So if A is equilibrium with B, A is equilibrium to C, so this B and C will be also in the equilibrium, and there is a calibrated lines and expansion we know. So accordingly it will give that your body temperature is 98 Fahrenheit or so. In this way we can measure the temperature. So this law gives the basics for the measurement of the temperature. Now I will discuss about the question number 3. Summarize first law of thermodynamics applied to a cyclic process. So if we apply the cyclic process, so if the first law of thermodynamics states that energy cannot be created or destroyed. It can only be converted from one form to another. So it is a conservation of energy. Means energy is cannot be created and you cannot destroy it. However, it can be transferred or converted from one form of energy to another form, one of level to the another level, but net energy will remain constant. First law of thermodynamics is applicable to all processes irrespective of whether they are reversible or the irreversible process. So first law is useful for all, maybe it is reversible or irreversible processes. The work done by the system and the heat added to the system vary with the path taken. So by which way you are doing the work and the heat supplied or heat aided, it depends upon which path you are going, and that path is called the process. However, the difference between the heat aided and the work done by the system is the same for all paths. But the difference between W and the Q, or del Q minus del W, is a constant whatever path, and in this way we have got one new property. That property is called the internal energy U. So this U we have obtained by the help of the first law of thermodynamics, and so here we can see the constant difference represents the change in internal energy between the two states, that is called the delta U. So the first law of thermodynamics says that when a system changes from one state to another, the change in internal energy equals to heat aided to the system minus the work done by the system. So we can write in this way that del Q is equal to du plus del W, or del Q minus del W is equal to du. Here we are writing du and here we are writing del. So del is not the property. They both are not the property, but this du is a property. This is the intrinsic property, and so we are writing the exact differential, and here we are writing the partial differential. This partial, this del Q and the del W, they are depend upon the which path you are traveling, but du is not. So the difference between the heat aided minus the work done is equal to du, and this du is the property of the material or property of the substance. So here we can see that del U is equal to del Q minus del W. So we have here, find the net work done by a gas around the cycle ABCA shown in the diagram. So we will see here that this is the diagram here, and here in this diagram, if you see here, this is here P and here is the V. Here it is A to B, it is going down at a constant volume. From B to C, it is moving at a constant pressure. So how much, and then it is C to A. So how much work done by this hatchet area? This, if you want to find out, how we can find out? We can find out this thing by area of the triangle. So what is the area of the triangle here? Half 30 minus 10. So this is the 30 and this is the 10. 30 minus 10 into 10 to the power 3. Into, here we have the 4 and here we have the 1. 4 minus 1. So here the 3. Here you have 30 minus 10 is equal to 20 is equal to 10. So here you have 30 kilojoule. So you have, this is the answer, that in this type of expansion where first process is a constant volume process, another process is constant volume process. So how much work is done? This we can calculate by the PV diagram, and this PV diagram shows that how much work is done, and we have here calculated that work is done by this process is 30 kilojoule. Now I will go for the next question, that is the question number 5. So what is the question is? A thermodynamic system is taken around the cycle ABCA shown in the diagram. Complete the following table. So we have to see that process, that this is the one PV diagram. PV diagram here, this is the pressure and here is the volume. The same type of question is here, but we have to see some more properties. Here it is 30 and here is a 10. So at process A to B, it is a constant volume process. Work will not be done. A to B. But from B to C, work will be done because we know that work is a PdV. So this work is equal to PdV. So here P is equal to 10 and V is equal to 4 minus 1. So work is done here. But there is a table. We will see here how much is heat in the process A and B, and how much is the work done, and how much is the delta U. So this we know that delta U is equal to Q minus W. So this we will see here that from A to B process, how much is the heat added and how much is the work done. So this work done is a 0 here. So we can see here that heat is here, A to B is cooling, means minus. So okay, net how much? This delta U if you see here, it is a negative. So here it is a negative, U is a negative. Now if you see B and C, here at a constant pressure, work will be done. So how much work is done? 4 minus 3. Okay. So here this you can see again, here B to C is heat is positive here, means you are adding the heat. And how much we have seen the previously that we got the 30 kilojoule. Okay, so we can find out that PdV, P is how much? It is equal to 10 into 10 to the power 3 and 4 minus 1. So we will get 30 kilojoule. This is the work done. So we got here plus, because it is expansion is taking place, work is done. It is a positive work done, and the delta U is also positive, minus positive, you will get the positive. So here you will see that is positive, here you will get plus 30 kilojoule, and this is also positive, it is given. So now from C to A is again the negative, this is the negative. Work done is how much? It is the 60, minus 60 kilojoule. So here it is a positive. So in this way, you can find out that how much and what type of heat is added and how much work is obtained and how much internal energy is obtained. So in this way, we can find out all this heat and the work. Now I will go for the question number 6. How much change in internal energy during adiabatic process? So what is the adiabatic process? The adiabatic process is the process in which there is no heat transfer from the system to the surrounding or from surrounding to the system. It is like an insulated system. In this type of system, if it is a reversible adiabatic, there will be no change in the entropy. Net change of entropy will be 0. So delta S will remain 0 in this adiabatic process, and it is an insulated process. That also we have to see it. So in an adiabatic change, there is no heat transfer between the system and its surrounding. Means this, if this is the system and this is the surrounding, it is like sealed one, like your flask, tea flask. So it is a system and this is the surrounding. So no heat will go, no crossing or no in and then no out. It will remain there. Heat, content of heat will remain there. So in an adiabatic change, there is no heat transfer between the system and its surrounding. From the first law of thermodynamics, we can say that if delta U is equal to delta Q minus delta W, this Q is 0. So we can see that delta U is equal to minus W. So in the adiabatic process, the internal energy, change in internal energy will be negative of change of the work. So if it is adiabatic process and if you know the work, you can find out the internal energy, and if you know the internal energy, put the minus sign, you will get the work. So that is the relation which we have to understand for any of our numerical problem or any application of this thermodynamic law. So here this, you can see the meaning of this adiabatic process. If you see here that here is the system, and this system, if you are putting some hot thing and all, it will be pressing it, but heat will not go, only work will be transferred. Okay, and this work will be equivalent to the internal energy, which, and this is the insulation which we have shown here, fully insulated system. And if it is like a piston and the cylinder of an engine, that also in the compression and the expansion process are assumed to be the adiabatic process. In that, heat addition and the heat rejection is not permitted. It is a fully isolated system. So when no heat is transferred, work done by the system decreases the internal energy, so the temperature drops. And so in this, what happened? In this type of adiabatic process, the work done by the system decreases, means it is a negative, and the internal energy so also decreases and the temperature drop will be there. So work done by the system decreases and the internal energy also decreases and the temperature also drops. Work done on the system increases the internal energy. So if you are doing on the system, or you are putting the work from outside, it is on the system. This is on the system. Work done, and this is the by the system. If it is going out, it is by the system, and if it is going in, it is on the system. So work done on the system increases the internal energy. So if you are doing here, delta U will be positive, and if it is going, then delta U will be negative. That is the meaning of this statement which we have shown here, that this shows that they are in the opposite nature. Work and internal energy, they have the opposite nature. Now we will discuss about question number 7, that is how much change in internal energy during constant volume process. So this we have to see here, that how much energy is there in the constant volume process. So since the volume doesn't change, no work is done. So from the first law of the thermodynamics, delta U is equal to delta Q minus delta W. This part is 0. So delta U will be equal to the delta Q. So the change in internal energy will be at the constant volume will be equal to the heat added or heat removed. If it is added, it is a positive, and this will be also positive. If it is removed, minus delta Q, so your minus delta U will be there. So added or the removed, the things will be same. So for the constant volume process, there is no work, and the internal energy will be equal to the heat added or heat removed. How much change in internal energy during the cyclic process of, so okay, we will see for the cyclic process. In a cyclic process, the system returns to its initial state, and so the internal energy is not changed. So in the cyclic process, delta U is equal to 0, and this is equal to Q minus W. So delta Q is equal to delta W. We can write that for the cyclic process, del Q is equal to del W. In this, delta U is equal to 0. So for the cyclic process, the change in internal energy will not be there. It is 0 because it is going in the same state and again it is coming to the same point, that is called the cyclic. So there will not be any delta U. So this change in heat is equal to change in work. The heat added to the system equals the work done by the system. Now the next topic is how much change in internal energy during free expansion. So what is the free expansion? You can see in this diagram that there is a chamber. In this chamber, a very high pressure gas is filled. This high pressure gas, another chamber, it is in a vacuum. There is a valve. This valve or stop watch or stop cock is there. If you open this cock, full very high pressure will enter in this, and it is a vacuum, so there is no resistance. And you know that by the second law of thermodynamics, work is done only when there is a motion against the resistance. But as a vacuum, we don't have any motion. As a vacuum, we don't have any resistance. Due to the non-availability of the resistance, here free expansion will take place. The free expansion will take place, and in this free expansion, there is a work will be zero. Okay, and also there is no heat addition. Q also will be zero. Only so here delta U also will be zero. So here this you can see how much change in internal energy. So internal energy will be zero. There will not be any change in the internal energy in the free expansion. If free expansion is an adiabatic change that does no work. So delta U is equal to delta Q also zero, delta W also zero, so delta U also zero. So we cannot describe it on a PV versus P versus V diagram. We cannot describe this motion in the PV diagram. Okay, now I will go for the question number 8. That is the small problem as we have discussed earlier. A gas undergoes a cyclic change ABCA as shown in the diagram. 20 joule of heat are added from A to B. B to C is an adiabatic change, and the net work done by the system is 15 joule. Find the heat added to the system in changing from C to A. So this you can see the diagram here, that a gas undergoes a cyclic change A, B, C and A. In this direction, it is moving in this direction. 20 joule of heat are added. So from A to B, 20 joule heat is added from A to B. B to C is an adiabatic process. So here delta Q, it is adiabatic. So delta adiabatic. So delta Q is equal to 0. And the net work done by the system is 15 joule. So delta W is a 15 joule. Area of this plot is a 15 joule. Find the heat added to the system in changing to C to A. So how much heat is added from C to A? This is our problem. So just we will go here. So this we can see here that delta U is equal to delta QAB minus delta WAB for this process, plus delta QBC minus delta WBC plus delta QCA minus delta WCA is equal to 0 for a cyclic process. Cyclic process. So this is the equation, and we will put the values which are given here. Delta QAB is given here, and so we can see here that delta QAB is equal to 20 joule. Here the work is 0. It is a constant value. So this is the 0 as it is a constant value. Then we have delta QBC. Here BC is equal to 0 because it is adiabatic process, plus delta WBC plus delta QCA minus delta CA is equal to 0. So we can see here that delta QCA is equal to minus 20 in this direction and plus delta WBC minus delta WCA. So how much in the BC and minus how much CA. So here we know this all the parameters. So BC we know and this we know. So here it is a 15. It is mentioned the 15 kilojoule, the difference of this. So minus 20 plus 15, we will get minus 5 joule. So the heat which is from C to A is minus 5 joule, means it is cooling the system. So this is the cooling the system. So like this we can find out the how much heat is added, how much work is done in each cycle. We can undertake such type of exercises. Now I will go for the question number 9. This state that discuss the perpetual motion machine of 1, why it is not possible. So we know that in the olden days people used to describe that I will make the machine which will not take any energy. It will just run without any source, without any fuel, engine will work. So such type of machines are called the perpetual motion machine. Those machines which are not following the first law of thermodynamics. And what is the first law of thermodynamics? Is equal to energy is conserved. It is a conservation of energy. Energy can be converted from one form to another form, but we cannot create or destroy. So that is the first law of the thermodynamics. So perpetual motion machine, that is called the PMM of the first kind, that is called the PMM-I, would be one to violate the first law of thermodynamics, to permanently produce useful energy or work without any energy source, or to produce more energy than consumed. This thus generate energy from nowhere. So that is the meaning that you start the engine and without fuel it will be running. You start the power plant, it will be continuously it is running. So they are not following the first law of thermodynamics. It means they are able to produce useful energy without spending any energy, or it is giving more energy, or it is producing more work than which you are supplying. So it is the violation of the first law of thermodynamics. Why is it impossible? That is the second part of this. So PMM-I states that work can still be produced in a cyclic process. This definition is against first law of thermodynamics and conservation of energy. So the above equation yields E2 is equal to E1. So it is not possible to construct such a machine. Now I will go for the next question, that is the question number 10. This says about intensive and extensive properties. So you know that the properties having a specific state points in a PV and the TS diagram, and they are not differentiated. They have the perfect differentiation. So we will see that an extensive property is a property that depends on the amount of matter in a sample. Mass and the volume are example of intensive properties. Mass and the volume are example of the extensive properties. And intensive property is a property of matter that depends only on the type of matter in a sample and not in the amount. So if you see that in extensive property like your volume, so if here we have the 10 meter cube, if you divide it, it will become 5 meter cube and 5 meter cube. So it is an extensive property. But if you see the pressure and the temperature, here P and T, and if you divide also, it will be P and T. It will not change. So those type of property which are not changing by its change of mass or the volume, those are called the intensive property, and the properties like mass and the volume, they will change its amount if you bifurcate it. So those are called the extensive properties. The two types of physical properties of matter are intensive properties and the extensive properties. Intensive properties do not depend on the quantity of matter. Examples include density, state of matter, and the temperature. Extensive properties do depend on the sample size. Examples include volume, mass, and the size. So this volume, mass, and the size is an extensive property. The density, the matter, state of matter, and the temperature, they are the, I think this is, now I will go for the question number 11. Define a specific heat capacity at constant volume. It is called the CV. So, specific heat at constant volume. So, the heat which it can store for a 1 cubic meter for 1 degree change of the temperature. So, we can define in this way that it is the amount of heat needed for a unit mass of a given body in order to change its temperature by 1 degree. So, if you, this is the amount of heat, that much amount of heat is required for a unit mass or per kg of the mass for a body to change its temperature by 1 degree. So, that is if it is the volume is constant, that we have to take care of. So, the specific heat of a gas at a constant volume is defined as the quantity of heat required to raise the temperature of unit mass of the gas by 1 degree when it is heated at constant volume. So, that is the CV. Now, we will discuss about the, give an example of the closed and the open system. So, what is the meaning of the closed system and what is the meaning of open system? That we will see here, and we have discussed in the first module that what is the closed system. In closed system, the only energy will transfer, but in the open system, energy and the mass both will be transferring from system to the surrounding or from surrounding to the system. So that is the difference between the closed and open system. If you see your turbine engine, they are the open system, and if you see your piston engine, they are almost the closed system. And so an open system can exchange both energy and the matter with its surrounding. The stove top example would be an open system because heat and water vapor can be lost to the air. A closed system, on the other hand, can exchange only energy with its surrounding, no matter. So, if I take a piston and the cylinder, this is the piston and this is the cylinder, and it is moving. Here is the one amount of matter, it is constant, but work and the heat, heat energy will go to the surrounding. This is the surrounding. This is the surrounding. Work and heat will transfer, but not the matter. Matter will be inside. How much amount is there? It will remain. This type of things is called the closed system. Closed system. And if this matter, if we have some valves here, like this, and these valves are making in and out, then it is a open system. Like pipe, flow in a pipe or anything, they are the open system. And so that is the difference between open and the closed system. Next is when do you say that the system is thermodynamically equilibrium in nature? So For a thermodynamic system to be in equilibrium, all intensive, that is the properties like temperature and the pressure, and the extensive thermodynamic properties like internal energy, Gibbs, then A, this is the enthalpy, entropy, these all parameters must be constant. So, all intensive properties and the extensive properties, if all are the constant, we can say that it is in the thermal equilibrium. Hence, the total change in any of those properties must be zero at equilibrium. So, there is no change of any this extensive or the intensive property, then we can say that the system is in equilibrium. Which are the three conditions for thermodynamic equilibrium? A thermodynamic equilibrium represents the state when all the three equilibrium, that is the chemical equilibrium, thermal equilibrium and the mechanical equilibrium are attained at a time. So, that is the best thermodynamic equilibrium. If there is no chemical reaction, it is stable. There is no change in the thermal properties and there is no change in mechanical properties. If these all things we are able to meet, then we can say that this is a thermodynamically equilibrium. So, in the next topic, we will be discussing about questions and answers of the module 2, that is the second law of thermodynamics, and we will see very soon for my next lecture. I am following these books, Eunice Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition. Also, I am following the NPTEL lecture from IIT Kanpur, which is mentioned as a 2. Any questions, you are welcome to ask. My email ID is ydwivedi@gmail.com. I also request you to do like and subscribe this channel. Also give any comments if you feel anywhere I need some improvement. Thank you very much for the joining. We will be seeing you soon for my next lecture, which is about discussion of question banks for the module 2, that is the second law of thermodynamics. Till then, thank you and goodbye.
Like, share and subscribe. Hit the bell icon for more updates.